What exactly changed when the world moved from OHSAS 18001 to ISO 45001, and why does it matter for your career today? Well, we are about to do a comprehensive breakdown of the structural shifts that redefined modern safety management systems. From hazard identification to proactive risk mitigation, this is the ultimate guide to that technical transition. But first, if you find this briefing valuable for your own safety awareness, please take a moment to like, share, and subscribe to the ISO Automation Labs channel. Your support helps us create more deep dive explainers just like this one. Okay, think of this as your official briefing. In a high-stakes industrial plant, safety isn't just a checklist, it's a fortress, built in layers. But how are those layers designed to protect against catastrophic failure? Today, we're going inside that blueprint, breaking down the critical systems that keep people and assets safe. All right, let's dive into this.
We're going to structure our briefing today around 5 critical layers of defense. It's a system, right? We'll start with the most fundamental principle, and that's simply distance. And then we'll build up, layer by layer, to the active systems and the protocols used during a real emergency. So let's move to our first layer and see how this all starts to build.
Okay, layer 1. The first and, you could argue, the most crucial layer of defense doesn't involve any fancy technology at all. It's simply about strategic separation. You see, preventing a single failure from cascading into a plant-wide catastrophe, well, that starts with intelligent plant layout. It's about thinking ahead. The core idea here is to create buffer zones. And I want to be clear, these aren't just empty spaces we've left for future expansion. No, these are engineered safety features. Think of it like creating fire breaks in a forest, but for an industrial facility. They're specifically designed to contain the impact of a potential fire or an explosion, basically buying you precious time and space to react.
And here's where it gets really specific and honestly kind of interesting. That number, 36 meters, that's not just a suggestion. It's the mandated minimum clear space between the boundary lines of major process units. Now you might be asking, why that exact number? Well, it's been meticulously calculated to reduce the risk of radiant heat, the invisible ways of energy from a fire, from igniting an adjacent unit. It also accounts for shrapnel or vapor clouds. For our high-risk areas, that 36-meter buffer is absolutely non-negotiable.
And this table right here brilliantly illustrates the whole system. It's not just about separating the main units. Look at this. Every single component, from a storage tank to a control room, has its own specific mandated separation distance. Let's focus on that massive 50-meter gap required between a process plant and LPG spheres. We're talking half a football field. Why? Because it's designed to protect against something called a bleave, a boiling liquid expanding vapor explosion. It is a truly terrifying event where the entire contents of a tank can flash into a massive fireball. That distance is your best, and sometimes your only initial defense.
Okay, so we've established distance. That's our first line of defense. But the next layer, layer 2, assumes something has gone wrong inside one of those units. So the question becomes, how do we make sure the plant's essential structures can actually withstand the intense heat of a hydrocarbon fire? And the answer to that is passive fire protection.
This quote from the safety standard really gets right to the heart of the matter. You know, we think of steel as being incredibly strong, right? But it loses its structural integrity alarmingly fast in the 650 to 1100 degrees Celsius inferno of a process fire. I mean, at those temperatures, a steel support can literally behave like a wet noodle, which can lead to a total structural collapse. This is exactly why we can't rely on the strength of steel alone.
So the solution is to apply these special fire-resistant materials, which is typically a specialized concrete coating. Now look at the difference here. A 2-hour rating is pretty standard for things like pipe racks. What that means is the structure can withstand direct flame impingement for 2 full hours before it fails. But for critical equipment that's holding large volumes of flammable liquid, we need a more robust 3-hour rating. That extra hour provides a vital, life-saving window for emergency responders to get in and gain control of the situation.
Now, beyond just fireproofing the supports, structural integrity also means containment. It's about controlling a spill. As you can see from these points, a diked enclosure acts like a big concrete basin designed to hold the entire contents of the largest tank if it ruptures. But just as important is the ground sloping. It's not flat. It's precisely engineered to direct any hazardous liquids away from other equipment and into a safe collection area. You're effectively starving a potential fire of its fuel.
All right, with our passive defenses in place, distance and structural hardening, we now move to the brain of the whole operation, the control room. During an emergency, this building has to function as a secure fortress. It's the one place from which operators can safely manage and shut down the plant. Now, for any of our units that handle things like hydrogen or light hydrocarbons, if the control room is within 120 meters of that hazard, it absolutely must be blast resistant. And let me tell you, this is not ordinary construction. It is engineered to maintain its structural integrity during an explosion, protecting the people and all of that sensitive control equipment inside.
And the engineering specification is incredibly precise. The structure has to handle a static overpressure of 3 megapascals. Now, what does that feel like? It is an immense, crushing force. A normal building made of cinder blocks or panels would simply shatter. It would become part of the debris field. This requirement dictates the use of materials like heavily reinforced concrete. So it's the difference between a building that stands and a building that's gone.
And if you look at these design details, you can see they are all about survivability. 2 exits, that's so personnel don't get trapped. Baffle walls at the entrances, those disrupt the blast wave before it can get inside. And look at this one, elevating the building. This is such a clever defense against heavier-than-air flammable vapors, which can creep along the ground. This prevents them from pooling and getting sucked into the building's air supply. Every single feature you see here is a calculated defense.
And here's a critical automated safety feature. To stop the control room from drawing in a flammable cloud, we have gas detectors constantly monitoring the air intake. They'll trigger an alarm at 25% of the LEL, that's the lower explosive limit, the absolute minimum concentration of a gas in the air that can ignite. But if that concentration hits 60% of the LEL, the system doesn't wait for a human. It automatically slams shut all the air intakes, ensuring the fortress doesn't poison itself from the inside.
So, this all leads to a really key question, right? If the area is unsafe and you can't approach the equipment, how do you shut it down? Well, the answer lies in remote controls, a vital part of this command and control layer.
Every single pump and compressor that handles hydrocarbons is required by law and by good practice to have a remote shutdown station. In the event of a fire or a major leak, operators can activate these from a safe location, like inside the control room or from a designated muster point, to stop the flow of fuel to the fire. This is the critical first step in gaining control. You are essentially turning off the tap from hundreds of feet away, starving the beast.
Okay, we've covered separation, hardening, and control. We're building our fortress. Now we come to our final layer, the active systems. These are the things designed to fight a fire directly. And this is all about delivering absolutely massive quantities of water exactly where it's needed, and doing it fast.
The firewater system, it has to be massive. We have to have enough stored water for 9 hours of continuous firefighting. Let that sink in. 9 hours. The total pumping capacity isn't just a guess, it's calculated based on a worst-case scenario. And as you can see from this breakdown, it's not just about the one tank that's on fire. It includes all the water needed to cool the nearby tanks that are exposed to the heat, and even more distant ones, plus all the reserves for handheld hoses. It is a system designed for the worst day imaginable.
Now, what's really fascinating here is just how specific these water application rates are. A tank that's on fire needs 10 liters of water per minute for every single square meter of its surface area to effectively cool it and prevent the steel from failing. But look at the pump house. It requires more than double that rate. And why? It's because of the concentrated risk of high-pressure leaks. You need that overwhelming force of water to suppress a potential jet fire instantly.
You know, it's not just about the volume of water, it's also about pressure. The system has to be able to deliver water to the most remote hydrant in the entire facility at this minimum pressure of 7 kilograms per square centimeter. This is what ensures our firefighters have enough force to project water onto tall structures and to overcome the intense thermal updrafts that come from a really large fire. Without that pressure, the water just won't get where it needs to go.
And finally, placement is absolutely key. Hydrants are spaced every 30 meters to make sure there are no dead zones where you can't get water. Those fixed water monitors, the big ones, are positioned about 22.5 meters from equipment for the best cooling trajectory. But they must also be at least 7.5 meters away. And that minimum distance is critical. It's designed to protect the operator from the fire's intense radiant heat, allowing them to actually get to the equipment and use it safely.
So, we have all these layers of defense. We have the distance, the hardened structures, the command center, the active fire systems. But how do they all come together in a real emergency? Well, this final section is about the most important part, the human actions that activate these brilliant systems. Let's just walk through the example of activating a fixed water monitor. You see a fire, your heart is pounding, but the procedure is designed for pure speed and efficiency under stress. You locate the right monitor, you approach it safely, you open the supply valve, you aim with the tiller bar. That's it. In just seconds, one person can get a high-volume stream of cooling water onto a target while the main fire crew is still assembling.
This is exactly how a well-designed system empowers a rapid response, turning a single person into an effective first line of defense.
And that brings our briefing to a close. We've seen how safety isn't one thing. It's a system of interconnected layers, from something as simple as distance to complex automated responses. The crucial point I want you to take away is that these aren't just rules in a book to be followed for an audit, they are principles that create real resilience. Which leaves us with a final thought to ponder. Are our systems just compliant on paper, or are they truly resilient in a crisis? True safety comes not just from having these systems, but from understanding how every single piece works together. Thank you for joining this explainer. To continue learning with us, please don't forget to like, share, and subscribe to the ISO Automation Labs channel. Stay safe out there.